Okay, so let's consider another problem. So we have a flat plate. Let's see here. It's got an angle of attack alpha. That looks good. So that's this angle of attack alpha. That's a flat plate right there. It's in a Mach 2.4 airflow. And the pressure is equal to 4.2 atmospheres. Which is not confusing at all. 2.4 and 4.2, that's not going to mess with me. No. Okay, so the question here is, what is my maximum pressure where I can still have an attached shock wave? Okay. So remember, in this case, my flow is being deflected. It is moving this direction, it has to move down. Because it has to move down, it is going to cause an oblique shock wave, like that. But there is an issue with this. There is an issue. The issue is everything is going to go horribly wrong. Okay, no. The issue is that at some point, if I keep on increasing my angle of attack, like I'm going to keep on being, attached for a while, but eventually it's going to detach. I'm going to have a shock wave going in front of it, just like if it was a flat surface in the flow. So, there's only some max deflection angle I can have before the flow no longer can do that. Okay, now let's talk about what deflection angle looks like for this flat plate. So you can see my angle of attack right there. That's pretty easy. And so you can also realize that the flow is moving in a straight line right here. And it has to then turn to be at the same angle as that flat plate, which means that my deflection angle is going to be equal to my angle of attack. Okay, that is the first thing there. So for this flat plate, my deflection angle is equal to my angle of attack. Okay, so we got some information there. So let's go ahead and start drawing on our diagram a little bit more here. So this will be theta, which is equal to my angle of attack. This angle right here is beta. And it's saying, what is the max pressure I can feel and still have it be attached? Now, you can already figure out, like, there's going to be some sort of limiting case here. So that max pressure is either going to happen when angle of attack is at a minimum, or it's going to happen when the angle of attack is at a maximum. Okay? Like, we don't know what the max pressure happens at, but we can think about this and figure out pretty easy. So if I have a flat plate that is infinitely thin and it's perfectly in line with the flow, is there any change in pressure as the flow goes past it, really? This is angle of attack equals 0. The flow is not disturbed at all, right? So P2 over P1, well, is 1 because it doesn't change. It's not changing at all. There's not even a shock wave. So I have to actually form a shock wave, which means since it's not 0, I'm going to find this max P2 over P1 when my deflection angle is a maximum. Okay? So alpha is going to be equal to my max deflection angle. That is what I care about here. So how do I find this out? How do I find this max deflection angle? We go to, not the tables, the theta beta Mach diagram. Yep, theta beta Mach. So I want to go ahead and pull that up and steal it in here. Let's see here. Boop. I'm going to chapter 9 where we find it. There's probably another place where it is. I just always forget where it is.
It's in the Feroki tables.
Oh, it's in the Feroki tables? Oh, it's in Feroki tables. I'm not going to worry about that right a second, but here we go. And it's the right one. Nope, one before it. One more time. Here we are. Should be down here. There it is. Okay. So this is the one we're going to deal with. This should be good enough for us. So I'm going to take this guy, I'm going to copy the image, and I'm going to put it into our problem. Because I can do that. That's the nice thing. Movie magic, everybody. Let's make it a little bit bigger, though. Okay, so we know that our Mach number is 2.4, which luckily for me does occur on this. So I'm going to go ahead and highlight that right there. That's 2.4. And I'm going to do what I usually do, which is I'm going to draw a red line going along this point, which I don't actually have to do because my max deflection angle is the deflection angle, which is simply right here at this edge. That is the max that can be deflected before it detaches. And so I'm going to just draw a line straight down from there. It's more or less between these two. Go all the way down, my best. There we go. I got it. And because I have absolutely amazing skills in reading these diagrams, I know, just from looking at it, and definitely not cheating and looking at the solution, is that this is going to be 28.7 degrees. Do I expect you to be that accurate? Of course. No, I don't. It's if you said 29 degrees because it looked like it was 29 or 28 and a half, because you're like, it's about halfway in between, that's completely reasonable. Okay, that's completely reasonable. So just do your best, okay? Do your best. You can realize that there is 4 in between each of these steps. So that right there is 2. That right there is a change of 1. And so you are able to get some precision from that. Just, do what you can. Okay, so I now know that theta is going to be equal to 28.7 degrees. But I want the pressure ratios. If I want the pressure ratios, I need beta, which is still fine. That tells me a lot. I can figure that out. Because if I want to know what beta is, I just go to this tip right here, and I go straight across. So once again, doing my best to draw a straight line. If you have a ruler, that'd be really helpful. If you don't have a ruler, get a ruler. And so that's roughly halfway between 60 and 70, it looks like to me. So that's 60 right there, that's 70 right here. And so I'm going to say that beta is equal to 64.5. Dr. Kidd, why were you so strangely specific? You said it was halfway between. Don't ask me. Don't ask me, okay? I know things. I know things. Either way, you just do your best, okay? You do your best to draw those lines. And if you have to, you get a calculator. You make a calculator for the theta beta Mach relationship, and you can just have it solve it for you. It's not terribly difficult to do. It's just, I'm not teaching you MATLAB in this course because we got a lot of equations we can solve by hand. That's the nice thing about it. Okay, so we know enough information here. First off, we already have part of the answer, which was we know that alpha is going to be equal to the theta max, which is equal to 28.7 degrees. So that part of the problem is already solved. We know what the max angle of attack it can have is before that detaches. The second thing we have to figure out is what is that max pressure? Okay, what is that max pressure? Because we know that P1 is equal to 4.2 atmospheres, and the pressure is going to jump up when it goes through the shock waves. So I want to know what P2 is. So we're going to need to go to our Appendix B to get that ratio. So we'll do that, but before we can do that, we have to find the normal Mach number. So my normal Mach number 1 is going to be equal to my Mach number, M1, times sine of beta. Will I keep on writing this out every single time? Yes, I will. Yes, I will. Why? Because you need to see it. I'm just being honest with you. That'll be 2.4 sine of my shock angle, which is 64.5 degrees. And that comes out to be a Mach number of 2.17. Okay, so that's not too terrible. And we can go to the appendices for Appendix B and start getting that value. Okay, so let's go to the appendix and get that value now. So I need to go to Appendix B. And I want to find P2 over P1 for a Mach number that's equal to 2.17. Here we are. Sadly for us, there is no 2.17 in this table. But actually it's horrible all around. There's 2.15 and there's 2.2. So I'm going to interpolate with you. Why? Because I care about you and I don't want you to have to do that alone, okay? Never interpolate alone, everybody. Never interpolate alone. So let's go ahead and I'm just going to copy this. Get the information I need. 2.17, right? Yes. So I need these values. There we are. I'm going to copy it and bring it in here. Whoa! I did not expect it to be quite that big. There we go. There we go. Okay. That was huge. What in the world? Okay, first off, this is Mach number, and this is P2 over P1. We're going to have to interpolate to get our value, because our value is somewhere in here. So when I'm interpolating, the first thing you need to realize is that you have to set one of these lines as low and one as high. Okay? So I'm going to set this one as low, and this one is high. As a note, this would be the point where I would say, if you haven't made a calculator, you can save yourself a lot of pain and suffering on interpolation by having one that you've already created in MATLAB or in your calculator. It's not terribly difficult, it just takes time. And for a lot of problems, you don't need to do it. Okay, so with that, low and high, I've got it, looks good. Now I'm going to start plugging into my interpolation equation. So here's how it works. As a note, I don't have to write P2 over P1 every single time. I'm just going to call that PR for pressure ratio, just to make it easier myself when I'm writing out this equation. Okay, there's nothing special about that. That's just for the equation. So I'm going to say that my PR, the pressure ratio, is equal to my pressure ratio low, okay, plus whatever I know, which is the Mach number, so Mach number minus the low Mach number, times pressure ratio high minus pressure ratio low, all over Mach number high minus Mach number low. Okay? So with that, I will be able to get my pressure ratio for this. Okay? I'll be able to get my pressure ratio. And so if you solve this, what you would get is that P2 over P1 is equal to 5.327. I'll just give you some color coordination here. So that's the low right there. That's the high. That's the high. And that's the low. Okay. So just trying to show you where everything is coming from. Whoop, I messed up one of them. That right there is not low, the high. There you go. Okay, everything else is good. And that's low. Beautiful. So with that, I have my pressure ratio. I can now plug it in and solve for what in the world is my max pressure that I can experience. It's going to be half to the shock wave, we know that. So P max is going to be equal to P2, which will be equal to P1 times P2 over P1. And that will be equal to my initial pressure, which is 4.2 atmospheres, times my ratio, which is 5.327, for an atmospheric pressure of 22.373 atmospheres. And cool. So we have everything. So we talked about what the max deflection angle is going to be, how we figure that out, because that's what's going to happen right when detachment is about to occur. We figured out the max pressure ratio we could feel, and we also did some interpolation for fun. Joy! So let's go to the next problem.